All right. Hey everyone, welcome. It's a pleasure to welcome today's lecturer and a visitor. And he's a friend. He's an amazing colleague. He did his first degree in theoretical physics in Cologne, I believe, and looked at gravity models. And then he went on, discovered neuroscience, and did his PhD where?
In Bochum.
Bochum, right? Okay. Then he spent time in Berlin, and then he spent some time at MIT as a visitor there. He was running the Amazon research lab in Munich in 2017. Then he's back at Munich. Back in Berlin, TU Berlin, and he's been really pioneering a lot of this work at the intersection of deep learning and grasping and manipulation. I also want to share with you a very big announcement. I hope it's okay to say this.
Don't know.
Yeah, but he has agreed to be a co-chair of Choral 2024, which will be held in Munich. So be nice to him, okay? All right, with that, I want to welcome Marc Toussaint.
Thank you very much, Ken, for the introduction. Yeah, so my career wasn't like super straight, but I think that's fun. So maybe also to others, it's actually cool to be in many different areas. So the original title of the talk was, do we need a cognitive architecture debate again? But I was creative over the weekend and thought also a bit about a different introduction. So let me introduce the talk a bit differently. So I think everybody knows this one, right? The model bird set. Don't know if you know this beautiful video. And I'll just let you zoom in a bit. I hope nobody gets dizzy or so. And while you watch this like beautiful video, maybe you can imagine that you're a scientist and you just observe this in nature somehow, right? And then you want to model that. And you wonder, how can I model that? Or maybe you can also, if you like, you can also imagine training a neural network to learn that set, meaning learning and classifying which pixel is actually part of the set or is not part of the set. I think these are interesting things to think about when you see the set. And it goes on and it goes on. It's really beautiful, actually. Okay. So, and I said these things. So imagine you're a scientist, you observe the thing here and you want to model it. And I hope you already anticipate where I'm getting at, right? So the thing we see here, that's the analogy of complex behavior, right? And we are we're sometimes scientists, sometimes we are engineers, and we want to model it, which means we want to describe it, to create it. And the question is, if you just see this or have an imagination of what you actually want to create, well, what's a good representation to modeling that? And also, I think actually interesting, I haven't anybody seen trying to do that. Maybe you want to do that. Can you imagine training a neural network to predict whether like a complex number is part of that set? And I have, I have no idea on either side, like if it's possible or not, but I just find it super interesting. The question though is, yes, Ken.
What's your hunch? Do you think that's feasible? It's actually a great question, and I think nobody tried that.
So first to do this with a flat architecture, I think this is where I'm also getting at. To do this with a flat architecture, feed-forward architecture, maybe not. But the thing is exactly, can you impose some kind of structural, some kind of computational structure, some computational priors, and embed that in the neural network? And then I think I think it could discover it. And the ultimate question is, would it discover like a representation which is as nice as that one, right? So everything you've seen in that video is described by that single line of symbols here, which is amazing, right? I mean, it's just a couple in ASCII code. It's, I don't know, a couple of bytes, that equation. And if you translate that to that image, it's like so much structure. I think it's amazing. And the question is, if you were a scientist and you observe nature like that, would you discover that equation? Or if you're in a neural network and you observe that data, would you discover that kind of equation? And, understand. And these kind of representations, I think of them as being implicit. They involve computation for decoding. I'm going to say something about that in a second. And I think of them as extremely powerful in terms of like generalization. And the core like message of the talk is that we want to have these kind of representations for complex behavior. And here is like some points that now relate to behavior, which is my view on why it's interesting to do research about reasoning. Because reasoning and planning is kind of like maybe not super on vogue anymore, because very often you think maybe it's easier to just throw reinforcement learning on it, or to just do behavior cloning and do other kinds of things. So, but really thinking of methods that involve reasoning, planning, inference, kind of are not that popular, but I think it's actually interesting. And when I think of reasoning, I think of this motherboard set, and I think of reasoning as the decoding of an implicit representation of behavior, like a very compressed implicit representation of behavior. And in that sense, you could also ask, what do the words goal and task and constraint mean? Those are the latent variables. That's the latent code of that representation. You see? So that's the latent code, kind of like the generative code. And if you would want to decode it, you have to do reasoning to actually translate it to behavior. Okay, so that was kind of my introductory kind of stage. This is not as cool as the Mandelbrot set, I think, but this is an example of the kinds of behaviors that we can create with task motion planning methods. Before I start any of these, this here, what you see is task motion planning, and it creates, I think, interesting complex behavior, but it creates it under the assumption of full information-based planning. So all of the things that you see here is not any like execution and simulation. So this is like really an open loop plan, if you want so, based on full information. So full information about the meshes, the models, and everything. So this is a classic, I don't know, we did a couple of years ago, the RSS, which we published. And this one is a larger thing that we do in cooperation with architects, which is about assembling like larger pieces of architectures with multiple robots. This doesn't look so impressive, but it's some like actually pretty complicated decision making. This involves a bit more like physics, physical context and stuff like that. This one is a little unpublished one, it's very small also. But this little creature actually takes a box and drags the box below that thing, and then eventually climbs the box and then reaches for the banana. The code, in case there's somebody else, Wolfgang Köhler, right? The cluster experience is more than that. So I think this kind of complexity of behavior is cool. But there are so many questions now that we like formulated algorithms to describe that kind of behavior. There are so many questions, and this talk is basically about questions about that. For instance, this one is just really full information-based planning, and the question would be how you could really execute that in a real world. So to get back to the more title and the abstract that I actually proposed for this talk. In the abstract, I wrote something like, perhaps we can think big again in robotics. And I think this is actually the case, because nowadays it seems with LLMs, I'm going to start talking more about LLMs also later in this talk, and also these TAMP-style methods, we can describe pretty complex behavior. And people in the field, they kind of dare talking again about general purpose, like general purpose LLMs, the idea that in LLMs kind of like latent understanding or knowledge to solve all kinds of problems is in there. Or general purpose physical reasoning and robotic manipulation, for instance, with TAMP planning, I described. So I think this is a great development in the field that we think about this general purpose problems again. And the original idea of that title, do we need a cognitive architecture debate again, is, well, it's about that point. So LLMs and TAMP, and I kind of see them analogous here, they are about high-level decision making. And they do, in that sense, therefore distinguish between high-level decision makings, the decisions about discrete things, about motor primitives or constraints, as we will see in a second, and the lower-level execution, which involves maybe motor skills, if you call them like that, or control primitives. So it raises the question about the right abstractions. And in this talk, actually, I do not want to like focus on the higher-level decision making, like the TAMP planning and so forth. but mostly about action representations and also later scene representations. Okay? So let's talk about action representations. And eventually keep the Mandelbrot thing in mind, because eventually it will get back to that like kind of stuff. But let's talk about action representations. So with the current work in LLMs, Secan, for instance, Clipboard, there's others, and in about 1 hour or so, there will also paper on archive with us as co-authors. I'll mention it also in a second. And also TAMP planning, task and motion planning. They assume that there is a library of skills, and the output of these LLMs is like calling these skills, so calling the motor primitives. And the same is also true for TAMP. We assume that we have this library of action primitives, this library of things to do. And to me, this is like the bottleneck for both of these areas, for TAMP and also LLMs, I think. It's not great. And of course, that raises the question, action representation, and also of these keywords like skill learning, skill discovery, state action abstraction learning, state action abstraction. I'm referring to George Konidaris kind of work. Maybe you know this work. So yeah, many people actually exist in work that try to also learn options in the context of hierarchical reinforcement learning. And that's been going on, I think, for decades. And I think our lab also tried to go in that direction and contribute something. I didn't list the papers because I think they didn't really go very far. So. And a classical conception of how you formalize skills and options and motor primitives is, by policy, and then you might have an initiation and termination. And the question, so I'm not criticizing all of that work. I think that's great, and people should continue doing that. But I'm wondering what is kind of an alternative view of representations on the action level side. And here is a more roboticist kind of perspective. Another video by Boston Dynamics. What's it called? Spot Mania, I think. Perhaps many of you know that video. I find that video actually super impressive. When I talk sometimes to others about this video, also my PhD students or so, they think, no, it's boring, it's like engineering maybe. They would say, or maybe somebody, some engineer just coded a sequence of primitives and maybe a sequence of funnels, and it's programmed and engineered and not interesting or so. But I find that behavior is super interesting also. Maybe not so interesting on the level of complexity as we've seen before with the planning kind of side. But the robustness and reactiveness, I think, is super impressive. And that's been done by Boston Dynamics, and people sometimes talk about it over coffee or something, but I haven't seen a proper theory paper or math paper describing that. And I think that's kind of missing. And I think it would be cool if we had a glue kind of between that more robotics kind of view of what is reactive behavior and TAMP and LLM. I think that'd be great. And this is what I want to propose or contribute. So my approach to that, kind of what I'm proposing is to think about more implicit action representations. So in that approach, implicit action representations, the high-level decisions actually are much more about objectives or constraints. So which objectives or constraints are active? And you can think of that as really very, very simple one-on-one robotics. If you imagine that you have an operational space controller and this kinetics controller, there's a couple of objectives. You could organize them hierarchically, and then you are really free to specify the objectives, and then the controller just, solves for it. And if we compare this to the more view of skills, so motor primitives, skill libraries, here we would think that we have actually a library of these functions, of these objective or constraint functions. By the way, if some of you here in the audience are more into inverse reinforcement learning or learning through demonstration, I'm calling them here objective and constraints functions that are going to be learned later, but they could very well also be reward functions. So you could think of that as being a library of reward functions. And a high-level decision, in a sense, are about which of these objectives are active right now. So this means that the decisions actually are functions that are being passed to the low-level control loop. And that's interesting. So really, a decision is a function, and that function is very often in our work so far hand-coded. Like I'm hand-coding the constraints of grasping, the constraints of pushing stuff in many demos so far. But we also have cases where these functions that are passed to a low-level controller are actually neural functions. They're being learned to train. And so the decisions are basically about which functions do I pass to the lower-level control loop, which is, these kind of functions. And why would I call this implicit? Because explicit means that I have an explicit model of which control to choose in a certain state. And implicit means that I have like this, this model where given this set of function defines an objective function, for instance, for model predictive control, some nonlinear mathematical program, and then the controls that are being sent to the robot are implicitly given by the solution of that nonlinear mathematical program, right? So again, it's like a computational decoding of the things. So this is the actual latent code that you provide the controller, and then you kind of decode it to the actual thing. That's why I would call it implicit. And if you relate this to machine learning, that's of course the same things that in old days, don't know if people even learned it like that in one classes. So you call it conditional random fields, or maybe you could also call it an energy-based model in machine learning, or just implicit functions. Right? So conditional random fields means that instead of training a network to really output a class directly, instead it outputs discriminative values like an energy function over these classes, and then the predicted class is the one with the maximal output, for instance. Okay, and why might you be interested in these kind of implicit representations on the lower model level? Well, one hypothesis is that maybe they're easier to learn. Maybe they're also easier to hand code than an explicit imperative controller in a sense. That would be the classical view why you use even MPC. And also, you might hope that with that kind of representation, you gain greater generalization and also compositionality. So compositionality is really interesting that, well, now you can actually have really compose these primitives. So it's not only about sequencing them, but also concurrently composing them if you have like a multi-agent system, for instance. Ken?
Mark, I just want to try to understand. So I don't see the view in this implicit model, but is you selecting from the MPC? I'm just trying to understand how to do that. There's this P to I active is a function that's activated, and then you do MPC on it. And I'm just unclear on that. And when you switch between the values, or it seems like there's a switching involved.
So yeah. Okay. So actually, there's going to be like proper math in some follow slides. But yes, this is a bit more mock-up. So the point is here that they have a couple of functions, and these functions define constraints that could be equality constraints in a nonlinear mathematical program, or they could also be objective functions, just some square potentials that you want to minimize some square error of tracking or something like that. And what I didn't note is that this this phi is typically a function of state, and the MPC typically looks at the short horizon of that state, and the short horizon of that state depends on the controls that you choose. So the U is here a shorthand notation for the controls that you send to a robot, and then we have a predictive model what kind of states that generates, and these states, on these states I have constraint functions or cost functions. Okay. So let's get a bit more concrete. So here's a particular piece of work, and it's just a small IRIS paper. It's very technical. I wouldn't say very technical. If you read it, it reads technical. But I think for me, it's actually conceptually an important missing piece, so that I was kind of missing between the TAMP that I had before and some kind of reactive and robust execution. Really. Let me show it. Oh, and also mention, by the way, that this is implementing this idea of implicit action representations, but actually not only for a single set of constraints, but a whole sequence of constraints. And I'll explain this in much more detail. Let's just watch a demonstration here. Eventually, the final constraint in the sequence of constraints is for red to touch green. And the controller kind of manages to find control sequences for red to touch green eventually. And there is a sequence of other constraints, like an approach constraint and pushing constraint, things like that. And you see this nice behavior. This one is actually the most important second in the whole video. Let me show that again. So here I'm perturbing a constraint which relates to the last stage of the sequence of constraints. And the perturbation of the constraint, which refers to the last stage, actually influences the the control, which is still in the first stage. So it's because the approach is here being aborted. It always aborts because it's seeing that something is not consistent with some constraint that actually happens many stages later. You also see that the controller is like completely compliant, and also can do collision avoidance, and it's pretty robust. And I think it looks cool.
Is this using vision?
No, it's using OptiTrack. A lot of the things, well, I hope I get to the part which is about learning, but this is still state-based OptiTrack. And so now this video was about 2 minutes. In these 2 minutes, you might have thought that what you see is a whole sequencing of primitives all the time, like a push, another push. And you might have thought that, oh, there might be a finite state machine that sequences all this stuff. Actually, in my view, what was happening here, you've seen a single primitive being active for these 2 minutes. And there was no looping, there was no auto for loop or anything like that. It was just a single primitive happening, like, that you've seen for 2 minutes. And that single primitive, there was no change in the high-level decision making, anything like that. And that single primitive was the solution to this MPC through a sequence of constraints, which I'm going to explain later. And so here, there was no switching happening in the terms of no switching of high-level constraints. We actually have another piece of work which also then switches completely strategy. But this one sticks to a single strategy. It's kind of confined in that strategy, which we also call skeleton. And within that strategy is executing what I think of as a single primitive, like a single MPC problem. There is another version in terms of demonstration about stacking, but for the sake of time, I'll leave it here. So you can just annoy the system with all kinds of perturbations. And yeah, okay. So let me explain that. We call this sequence of constraints MPC. And again, the motivation for this work was to think again, we have these cool, nice planners. They plan all kinds of complex stuff. But honestly, we had no concept of how to bring them on a robot. And this was supposed to fill the gap of how can you go from proper high-level decision-making to a proper action representation, which is reactive. And there is previous work on that. There's a really interesting one by NVIDIA Lab with Dieter Fox and others. But they actually use predefined controllers, but sequence them quite reactively. There is some work by Jeannette from Stanford. There's some other actually impressive work also from Freiburg that I want to mention. But let's get into how we formalize the problem here. So the assumption here is that the high-level decision provided by TAMP, by task motion planning, or by an LLM actually, is not only one constraint, like the next constraint to be done, but a sequence of constraints. And in the case that you've seen in the demo, that was just 4 steps, for instance. It's not a very long sequence. It could be 4 steps. So basically, the high-level decision is to say, you lower-level controller, please generate controls to fly through these constraints. I'm saying flying because like I intuitively often think of that as being like steering and flying through constraints. And we actually also applied it to quadcouplers. These constraints, though, are not like they live in submanifolds. They're nonlinear, so it's not really like gates when you fly literally with a drone through them. But it's just the generalization of that. So any constraint just defines a lower dimensional manifold, and you kind of fly through these constraints. And you tell the controller, find some kind of solution to go through. And actually, so the controller will maintain, I'm like explaining what I'm going to show technically in a second, the controller will maintain waypoints which are consistent to these constraints. And whenever something is perturbed about the last constraint, that is maintained with a very high frequency reactively. And if something weird happens with the last constraint, that directly propagates to all the waypoints on the earlier, and also informs, for instance, that an earlier kind of constraint that was met is now broken again. And you have to kind of like backtrack. And so the controller is really maintaining this not very long, but this estimation of the waypoints of the next like focal points. Okay, some math. It's actually not so complicated math, but it's just a standard like MPC formulation. So we have a control objective, and the control objective here is just the cost. We want to minimize cost over the trajectory. Xi here is the continuous time trajectory. That's standard. It's actually time optimal. And honestly, with this work, the first time I got into touch with time optimal control and proper timing optimization, and it's cooler than I thought, and also much more challenging than I thought. And actually, a lot of the technical stuff we solved in that paper is about the timing optimization. And I actually believe, maybe it's because it's novel to me, but actually timing is so important for manipulation, which I didn't maybe properly realize. So, but everything about the compliance of manipulation is directly also related to timing, because your estimate of timing when you reach a constraint like a grasp or when you reach a touch or so is directly related also to your compliance and the gains and everything. And so reactively updating your estimate of the timing of when you reach constraints is actually super important for very fluent and also compliant manipulation. Okay, sorry. So it's timing optimal. So the total timing is here part of the objective. Then we have the start constraints, and then these last two lines are exactly like these waypoint constraints. And we might have constraints about the waypoints themselves, and also running constraints, which might be constraints on the state and also the velocity. That's why it's underlined here. Solving that full MPC over the full horizon, that would be too costly to do in a reactive loop, and so we decompose that. And so in every MPC cycle, which is 10 Hertz, which for control theory people is not a lot, but it's good for us, I think. So with 10 Hertz, we managed to update all the waypoints, and that's like they account for the long-term interdependencies of all the waypoints of grasping and pushing and where you have to push in order to get there. So this is really accounted for long-term dependencies, the timing then as a third variable, and then the receding horizon. And the MPC cycle is doing like a coordinate descent. So it's assuming timing and fixed and optimize the waypoints. Then it's assuming waypoints fixed and it's optimizing the timing. And that makes it, efficient. Right, I think I sketched that. So this is the MPC cycle eventually with about 10 Hertz. I didn't mention actually a detail, and this is the detail about this backtracking, which leads to that reactive pushing. And because maybe you might think that this requires like a major part of the algorithm, like a major thing. But actually in this framework, it only required like literally a few lines of addition to get this reactiveness in there. And because what this MPC cycle also has to maintain is just a counter of which constraints are still ahead. It simply needs to understand which constraints are still ahead. And then if one of these constraints are being lost, so you have like an equality constraint in the approach direction and the push direction, if that is lost, then you backtrack. And that's a couple of lines that you kind of add, and you get this reactiveness in the MPC controller. You could actually, I had this some years back when I was talking about TAMP planning, and people asked me, can you execute this in robots? And I always said, yeah, but just open loop. Or just stupid trajectory tracking, which isn't very robust. And people then always ask, can you not just do replanning? Because that's the standard conception. You have a planner, want to get a reactive, just to continuous replan. And I think that thought is perfectly fine, but to do full-fledged replanning over all discrete decisions in real time, that's just too much. And if you think about it and iterate that thought that you just do replanning, and how could you get replanning efficient, but only within, like with fixed discrete decisions within the skeleton, actually, I think you might end up with that thing here. So in a sense, you could think of this here as being a form of continuous TAMP replanning, which though takes control serious because it also talks about timing. So the TAMP planning actually really ignored timing, but this control loop here really is very serious about timing. And also approximates things to waypoints and everything to get it done in real time. Okay, I'll skip over that quickly. There's more details in the paper. I think I want to go a bit faster, so I just skip that. There are some also technical things that I can show and so forth. And I showed you also the demonstration already. I think I'm going to skip this also for the sake of time. Just contact me if you want to know more about this, and there's also like some more demos and videos here. Okay, so this was a bit more detailed, like concrete work. So let me zoom out a bit again and get to a high-level discussion. So here, high-level decisions, actually what I'm proposing concern a sequence of constraints to be realized by the lower-level action sequence. And that is an implicit form of action representation. And the controls, that's an interesting aspect. The controls actually also depend on higher-level decisions that concern the future, like the controls now. And I think I mean, I don't want to overstate like differences too much and so forth. All are fine like frameworks, but I was thinking like, how does this actually now relate to standard options and standard hierarchical reinforcement learning and sequencing, like things like that. One difference is between explicit and implicit. Okay, fine, we discussed that. Another difference, it seems to me, is that thing like in skills, it would be very hard to design a skill or an option which has a controller, which actually depends on some high-level decision, which is like 3 steps in the future. Because the skills in hierarchical reinforcement learning, they are strictly hierarchical in temporal sense. Like the skill depends only on the abstract decision now. And that's, you know, by definition, by construction of the formalism, it's a semi-market decision process. And so there is no real information propagation from future decisions to some parameters of the skill now. But this framework it's actually like different. Just for those of you that have heard about planning as inference, and I've had a phase in my career where I was thinking a lot about planning as inference. This idea of having controllers, which, you know, if you constrain them on things you want to see in the future, like goals, sub-goals, other kinds of constraints, and then having a controller that infers what is an action consistent to all the future constraints, that's been around with me for quite a while. And what you've seen or what I've showed is an instance of that, but it's not using probabilistic inference, but nonlinear mathematical programming to actually infer these actions. But it's just a different computational tool in my view. But otherwise, it's actually quite consistent to that idea. Okay, now let's try to move on. I need to look at the time. So is this now an interesting action like representation on a lower action level? Maybe also for LLMs, and so I think it inherits a strong generalization of MPC, which is great. So MPC, you can include collision avoidance or translation invariance, or if the MPC it doesn't really matter where the object is. So if you define the constraints to be relative to the object, the MPC will solve it for you. I think it's also like strongly generalizing in the sense of compositionality. Just you can add more constraints to the same MPC problem, for instance, for the left and the right hand at the same time, and it's not easy for it to do that. But so far, everything you've seen, like these constraints, I coded hand-defined, and I became really good at this. Like over the last 15 years or 10 years, I'm coding constraints all the time. It's programming, right? And students often actually have a hard time to do that. And I'm trying to tell them, like, to teach them that I don't know, it's just a thing. It's almost like a programming language. You have to get used to how to program these kind of constraints. And that's, of course, not the way to go. Eventually, yeah, you would have to like learn them. And so instead of like skill learning, we end up with a problem of constraint learning. So can we extract these constraints from demonstrations, for instance? And I'm going to get there actually next, going a bit quicker. So the question is, what should be input to this high-level decision-making and control? In the TAMP setting, in the planning setting, and also in what I've showed so far in the control setting, we assume the full information setting, which means that everything is known to the system. Like some people also call this the privileged setting. So you have full model knowledge, shapes of everything, but full state information. There is no uncertainty. At least you don't. In our planning, we don't really account for uncertainty. So, and for that reason, there's no need for perception, and actually also not for control within that kind of full information kind of abstraction. So that's what we assume in TAMP setting. In Sequential or the existing LLM models, typically the input to high-level decision-making is just textual scenes. the textual scene descriptions and so on. So it's missing out that direct geometric information, which actually our TAMP planning is pretty strong in to account for geometric information. So the question is like what kind of inputs we could like learn to use in that case for higher level decision making, or for also for this control methods, which exploit this kind of the 3D space and structure. And there is different views on that. So yeah, maybe one comment. So eventually where we want to get up with is that these constraints, the 5 functions that we use for control and also for planning, by the way, that they are image-based. They shouldn't be state-based anymore. But eventually they should just be based on sensors. And we should hand over to our MPC loop, we should hand it over like a function which is image-based, so that the MPC can really work with the image-based constraint function and to have a reactive loop which is actually closest to perception. And now you could just train these constraints on the images, but actually in the last years, I kind of followed another approach. And so frankly, I'm not sure if you have to think of it like that, but this is how we approached it. So we thought of it that it's really interesting to exploit 3D structure by trying to learn field representations of objects. What does that mean? So instead of like representing the field in terms of meshes for information based, or representing it only as a 2D image, which is completely unstructured, we are kind of in between and say, let's represent the scene as a set of fields. So every object is represented by a field. And a field could be like a neural descriptor field, or a NUR field, or a sign distance function. Or what we work with is this pixel-aligned implicit functional object I'm going to describe in a second. And this kind of like field is 3D embedded, so it does represent the notion that objects have localities, and that only objects might interact when they're actually close and local, and the fields actually overlap. But it's abstract and learnable. The idea then is, there's 2 instances. Danny Dries was leading like quite some work of that, also postdoc of mine, Chang-Soo Ha. And I'm only going to talk mostly about this one here, where based on these fields, we learn task constraints. So this means we represent this scene as 3D fields. Every object is like a field, feature field in this 3D space. And if we now ask, where can we grasp this object? This is now actually on much more experts in the design. Where could you grasp this object? What you do is you probe this field, you query the field to some reference points at this gripper. And these field signals at the reference points, you map them with an NLP, with a neural network, you map them to discriminator for successful grasping. And if you did that, then you have, this is the file, this is the constraint, right? You take images, map them to fields, query the fields at the gripper point, and map this to the signal phi, and if the phi is 0, then it says successful grasp, and if it's non-zero, it's not a successful grasp. So we learned the discriminator for successful grasping. Right, so basically the high-level decisions is about passing these functions, and now we're going to implement these functions actually with neural networks. I think I'm going to be a bit quick on that one. So it's kind of like similar, I think, to how other people did that. In particular, also neural descriptor fields is quite similar. But what's happening is we take multiple camera views, and these multiple camera views take images, and we assume that we have also the camera calibration matrix. So we know the extrinsics of the camera, and intrinsics anyway. And we want to learn a function, a constraint function, which is completely perception-based and indicates successful grasp or successful hanging. Also, we're going to see that in a second. The detour we're going to make is that we're first going to train a feature field representing an object, and that's using a new net for every image separately to embed the image or process one of these images, and then it's querying the output of the new net at a pixel point which corresponds to the 3D query point. The 3D query point is the query point that the gripper, for instance, defines. And then we're going to average all of these, and this gives us a field. And then we're going to probe that field at different reference points of the gripper and map all of these field values, so field signals at these reference points with another nonlinear function onto the actual discriminator. And that one we're like literally going to use within MPC or planning, right, to define a constraint in a nonlinear mathematical program. So this one definitely needs to be differentiable and smooth, but we managed to do that. So this defines a pipeline, and now the question is how we train all of this stuff. So this defines, in a sense, an architecture. Now, the question is how we train that. And because the field representation is actually quite hypermetric, we want to have like a cheap supervision data for the field representation. And we do that by training the field representation to be sufficient to decode the distance to the object. And that's other people have done that, and nerves is also like similar. It's a very strong supervision signal when you require the field representation of an object to be at least sufficient to decode the distance to the surface. And that's very cheap, like supervision data. And that's how we get a field representation, and then we freeze the field representation. And on top of that, we can like learn a head. And the head is now about discriminating successful grasp or successful hanging, as you will see in a second. And getting supervised data for this problem is harder. We actually do that in simulation. So in simulation, we generate like tons and tons of graphs and just shake and see if it drops. It's that thing, as you did, as many labs did. We also generate tons and tons of possible hangings of a mug and check whether it was like successful. And that gives us positive and negative data for successful graphs or unsuccessful graphs and hangings. And that one renders the learning of our constraint finally as a supervised problem. So this is really now just a discriminator of the successes in simulation. And that's, when I earlier said going from skill learning to constraint learning, that's how I think about it. And again, not overemphasizing differences. It's really similar to reward learning from demonstration or also in with reinforcement learning, but in that framework of constraints for TAMP planning or MPC control. And here is a demonstration. So that's a paper where, is that running? Yeah, it's running. Jiangsu, the postdoc, was actually leading, where it's grasping mugs and then hanging them. And both the grasp was a constraint that was learned based on images, and this is executed here completely based on images. And the same also for the hanging. Both of these constraints completely defined only on 3, I think, camera images. Define that differentiable function phi that is being passed to an optimizer, a nonlinear mathematical programming solver, and that generates in these constraints. And the discriminators were actually trained on a class of cups. That's why I was generalizing, but only within a class, which I find quite limiting, and for different positions of time. Okay. Let me get to the discussion. We only have like 5 minutes left, I think. So we end sharp at, or, okay, I'll try to be like super fast. So I think of that as being still pretty preliminary. There's so much more for us to do to actually learn these constraints so that we don't have to hang code them. But I think this is kind of illustrating thing. We did similar things for learning constraints for prediction, like dynamics constraints. In about 15 minutes, there will be a paper on archive with many authors. It's pretty cool, with many authors from Google and also like me and others. And it's a large language model which outputs, which uses our TAMP planner to make an LLM to output the same as our TAMP planner. But the cool thing is that it actually takes geometry as input, not just text, but this LLM, it's not anymore an LLM, it's what they call an embedded language model, embodied, interesting word. Anyway, so it takes images and state information and geometry actually as input, not only words, and can therefore be trained to do proper geometric actually reasoning and kind of output the same as TAMP otherwise. Discussion slide. So really quick. So I staged the whole talk initially with this Mandelbrot thing, right? And kind of like saying reasoning as a decoding of like an implicit representation of behavior. Two like comments on that on a high level and the lower level. On a higher level, do we actually need that kind of reasoning? I think it's a really interesting question. I think we need research on TAMP for us, for ourselves, to better understand like the structure of sequential manipulation. So I think that's a major actually motivation for me to actually do research about it. I also think that the kind of generalization that TAMP demonstrates is great for us to guide where we want to get to, so to define a target, but the TAMP planning itself maybe will not run on the robots in 20 years, like the full-fledged TAMP planning. But still, like the way I see it is the following. So on the other hand, you could think of, let's not do like model-based reasoning, but just learn everything, and that very much nowadays goes in the direction of LLMs. They can exploit massive data, and also you can train them to be sensor-based, as the archive paper. But still, you could then think, are LLMs, are they going to actually be used as heuristic for TAMP planning, as with AlphaGo, if you think about it? Or the other way around, can you use TAMP planning for data generation? And I think both of these directions are super interesting. And I still would think that involving some kind of reasoning mechanisms to eventually make high-level decisions and combining them with LLMs actually is super interesting. And on a lower level, I talked about implicit action representations, the MPC loop. And actually are happy that it seems to me that the field and also we are trying to again discover supervised learning problems for model on the model side rather than relying too much only on reinforcement learning. And that's, I think, also a direction which is super promising. Try to find all kinds of formulations where you end up with a supervised learning problem. Okay, thanks for your attention. I hope I'm still in time. And how many minutes do we have for questions?
Well, a couple minutes for questions. Good. Maybe I can start by asking, I'm curious about the class of tasks. Can you say a little more about the tasks that you can foresee? Because in the abstract, I'm sort of unclear. Like, do you think of it as tasks that have longer horizons, like assembly, or what kind of tasks are you thinking?
So actually, the long horizon thing or the complexity in terms of the TAMP planning thing is not so much what I'm actually right now most interested in, because I feel if we have like full model-based knowledge, then it becomes a matter of classical heuristics design. So designing good heuristics to get actually the long horizons that we want. In terms of tasks, actually, I'm thinking about like really general purpose low-level manipulation. So meaning that the kind of constraints and kind of manipulations that we can involve and represent in planning involve any kind of low-level manipulations of objects, like balancing, that's really hard, or like turning like this, like all kinds of manipulations. And the question still, which is really hard, is how to discover these things. And in order to discover these kind of things, I think there's really interesting work in terms of skill discovery and representing skills, and also using classical options and skill frameworks to discover all possible like physical interactions with objects and so on. And I'm wondering whether we could contribute to the same kind of question with different representations on the action object. And I think this is where I would want to get at. So the task should be to be able to plan any kinds of physical manipulations, not only those that where we pre-coded kind of the classes or the primitives or the constraints.
Okay, so you actually learn the options.
Learn them, but it's classically you use the word like discovering them, right? If you learn them again from some pre-specified batch of data, supervised data, you had to predefine already the concept of grasping or the concept of hanging and so on. But the question is whether you can discover such a library of constraints such that if you use that library of constraints, you can create all kinds of crazy physical constellations.
Okay, good. I mean, I just think about something like untangling a cable or something. I mean, I'm just wondering, like that's a long horizon task, but you don't have a pre-existing model like assembly. It's sort of a disassembly. But I'm just curious what kind of primitives would be useful there.
I would also be super curious, and whether you could discover these primitives rather than coding them, right? Yes, and again, I think I'm super bad with like cables and ropes and flexible things.
Yeah.
So I would have a tough time with that. But even with rigid bodies, there's like really unexpected ways you can manipulate rigid bodies. And some of them are super useful and some are not. And really discovering those, I think that's the thing to be solved.
Good. Yeah. I have a question. Let's say you were introducing your library of constraints to these semi. In terms of compositionality, which you mentioned, so I think in the example there was a sequential compositionality. Do the concept class of constraints that you considered, at least in the paper, does it also enable like parallel composition of these constraints and so on?
Yes, yes. So when we program systems, so there's supernatural ways of parallelization, for instance, with the left hand and right hand. So if they do independent things, you can just impose one constraint in the right hand at the same time left hand. In little student exercises, so we also like put crazy constraints that should balance the buttle on the elbow while grasping at the same time or so. And these kind of compositionality is like easy to realize. Yeah, it's kind of easy to realize. The question would be which ones are actually relevant and which one are also relevant for more versatile manipulation.
So I have a question about the work of first learning the genetic field and then learning the constraints. I find that like very interesting because it kind of reminds me of how baby learns because they develop through the structure and then they learn to pass and they fail. But it also kind of made me wonder that this kind of success or failure data, we might never be able to acquire them just from like data on the internet because only us know, only we get our own sensor data. So I'm wondering if we'll ever be able to train models.
I totally agree, and it gets again to that same thing. So I imagine people know motor babbling, right? So motor babbling is like random motor exploration. That's not very interesting to explore and discover all possible manipulations in the world. So I'm actually wondering what is a more interesting type of babbling. There is also goal babbling. Maybe also do constraint babbling. I'm not sure, but I'm wondering whether there could be some type of exploration, autonomous exploration in a simulator, which would create and with good chances, not non-zero chances, actually create very interesting manipulations, and use those then kind of hindsight then as supervised data to learn the constraints. But I think the question there is still the interesting exploration. And I don't think that standard like reinforcement learning, epsilon noise, or motor babbling is the answer to that.
A bit along the same lines as this question on the constraints, which are all interdependent, basically, or dependent on the final constraint. How did you model this dependence? Was this basically an MPC, and then you kind of had a model of how it can move, and that's how you got the intermediate steps? And also how, because I saw you talked a lot about the timing and also basically having a plan for the timing. How do you take that into account? How do you model that?
First, these constraints actually could couple any kind of waypoints. I didn't describe it in all generality actually. So, but there is, for instance, one constraint that where the pushing approach should be aligned with a vector, which is collinear with where the object eventually ends up in the third frame, or like waypoint. And that constraint is super interesting because it refers to a position in the third waypoint, which hasn't even been computed initially, but it is being solved by the solver. And once it is being solved by the solver, it defines actually a constraint in the first phase. Mm-hmm. And because these constraints can arbitrarily couple all of any waypoints or features of any of these waypoints, you can create any kind of interdependencies. And the other question about the timing, I didn't have any really constraints about timing. That's really just timing optimal control. So it finds the timing which is least cost and as fast as possible. Really assuming standard control theory notions of timing optimal control.
It was not done in your constraint computation, it was like a separate.
First, for instance, in TAMP planning, in the offline planner, timing was completely artificially handled. We assumed like rigid timings, so super unrealistic. And also the typical constraints are usually only coupling geometric constraints, and they don't care so much about timing. The timing is really like the complementary thing that suddenly then comes from the control side to try to fulfill all of these geometric stuff with most fluent and time efficient.
Okay, any more questions? Because I'm gonna have to take them away, so why don't we translate it? So this is your chance. All right, one last question.
And a very quick question. What is the boundary between a low-level scale and a high-level scale? So what's in this motion primitive? Like take your form or move 1 meter, move your joint in 1 meter.
Yes, yes. That's a super interesting question. I sometimes feel like if we had a really good answer about that one, that could bootstrap all the discovery of skills. So in the TAMP planning, which the formalization I call logic geometric programming, there is actually an answer to that. And this answer would be that ideally, if you have a very, very complicated optimization problem, you would like to introduce discrete variables to enumerate local optima and make the subproblems convex. Right? So if you have a very, very like non-convex, nonlinear mathematical program, ideally, if you discover like symbols, discrete instances or enumerations of all the convex regions, so that's like an ideal abstraction. Because then you perfectly decomposed it into a hybrid problem or a mixed integer problem where you know all the subcomponents are convex, and then you know the rest of the discrete stuff you have to do by discrete search. And if so, it's a bit idealistic, but if you would stick to that, then I would say you put everything in a lower level model control level, which leads to convex MPC problems. And why? Because that's where convex MPC is super, super strong. Generalized is super strong. That's perfect. You can do this perfectly, right? And then the high level decisions, they have to deal with the non-convexity actually, which very often is arises from what do you want to interact with, because both of these are completely different local attractors. Yeah.
Okay, great. Thank you so much, Marc.